Hello and welcome to today's class on DC. I'll share my screen, share the PPT. Somehow I am facing some problem in sharing the PPT. Okay. Are you able to see the PPT? Okay. So today we'll move to a new topic, that is pseudo noise sequences or PN sequences and spread spectrum communication. So these are some topics in advanced communication systems that are used nowadays. So this is part of module 5. Okay. So far we have learned about QSK, PSK, all normal digital modulation schemes, general digital modulation schemes, and their error probability calculation, bandwidth, and power spectral density. Those kind of details we had looked into. And today we'll look into pseudo random sequence or PN sequence and how it is generated and what is the application. And in next few classes we'll look into spread spectrum communication, where this PN sequence is utilized to achieve certain good characteristics. Okay. So this PN sequence is nothing but a random binary sequence consisting of ones or zero in direct digital form, or +1 or -1, or plus V and minus V in the polar form. It's a random sequence. Basically, its application is in spread spectrum communication. We'll come go into detail later what is spread spectrum. Actually, this was initially developed for military applications like military communication, secure communication, and guidance. Guidance like global positioning, GPS, global positioning system, and radar system by the US military. So our GPS uses the spread spectrum communications transmission. So as I mentioned, it is a binary bit sequence generated using flip-flops and XOR gates. Basically, the basic basic concept that is used is something called LFSR, linear feedback shift register. So it consists of flip-flops and XOR gates. And this is actually not exactly random, but it is pseudo-random, because by seeing the circuit, you can actually predict the output sequence. But you need to see the circuit, or you need to see some polynomial equation that describe the circuit. So if a person know that the output sequence is predictable, but otherwise it is not predictable. That's why it is called pseudo random sequence. And it has many, or it has most of the useful properties which are required for spread spectrum communication, secure communication. Okay. One minute. Is there any problem in the presentation? Are you able to see it? Okay. I'm seeing two presentation in my. Okay. So I talked about the LFSR, linear feedback shift register. So that I'll show you what a linear feedback shift register is initially. So this is an example of a linear feedback shift register of order 5. So it has 5 flip-flops, FF1 to FF2. So flip-flop will have a clock. Generally, it will be edge triggered. During the positive edge or negative edge of the clock, the flip-flop 1 transfers the data from input to output and then keep quiet. And these plus signs are XOR gates, or we call it as modulo 2 addition. So this is an example of a LFSR, and this output sequence will be a pseudo random sequence. There are certain conditions and there are certain properties. We will be looking into that. Okay. So these are characterized by, okay, I'll go to. So this is a circuit, and this circuit is characterized by something called a generator polynomial. So the maths behind that is a little bit elaborate and complicated, and that is beyond the scope of this lecture. I think that is not mentioned in our syllabus also. So we'll talk about how the generator polynomial is made from this circuit, or how the circuit is made from the generator polynomial. So the maths involves some Galois field, some advanced topics like Galois field and arithmetic in Galois field. Okay, that we are not going to deal in this lecture. Okay, so basically, so the generator polynomial with degree, which is equal to the number of shift registers in the PN sequence. So in the picture I have shown, there are 5 flip-flops. So the generator polynomial will be a polynomial in Z, that is having a degree of 5. So I'll show you that example again. Here the generator polynomial P of Z is Z raised to 5 plus Z cube plus Z square plus Z raised to 1 plus 1. Okay, so we'll come to we'll understand how it is made and how we draw the circuit. Okay, and this is used to represent the structure of a PN sequence generator. And we use the modular, the plus in the equation is actually modular 2 addition, and that is related to how it has come. So from where it has come from is from the Galois field theory, GF of 2 theory. And another important thing is for the PN sequence generator, shift register is described by the generator polynomial, which is actually the polynomial has to be a primitive binary polynomial in Z. So we'll see what is primitive. So the PN sequence generator needs to have some properties to be used in the spread spectrum. One thing is, the first and foremost thing is, it has to be maximum length polynomial. That means using n number of flops, you need to get a sequence of length 2 raised to n minus 1. That is the maximum length possible using n flip-flops. So to achieve that, you need to have a polynomial, or the circuit needs to be represented by a polynomial that is primitive. Primitive means it cannot be factorized. I think all of you know how to factorize a polynomial. So primitive polynomial cannot be factorized. It is like a prime number. Prime number cannot be factorized, right? Prime number 7 is a prime number. That means its factors are 7 and 1. Like that, a primitive polynomial is a polynomial which cannot be factorized. Its factors are 1 and the same polynomial. Okay, that is what is mentioned here. And the generalized polynomial, I'll give you 2 minutes to read through this. The third point you may not understand now, I'll show in the next slide. Okay, I'll go to the next slide. So this is the general structure of generator polynomial and the corresponding circuit for an LFSR. So these plus are actually XOR gates. Okay. So this is the first flip-flop, FF1, 2, 3, up to FFN, or FF in this case, FFR. So the general structure is you have R number of flip-flops, and output of all those things are connected to, means are XORed and fed back to the first flip-flop input. Okay. So what are the characteristics of an XOR? For same inputs, output will be 0, and for different inputs, output will be 1. That is the basic characteristics of an XOR, A bar B plus B bar A. So here, for this circuit, the generalized circuit, the polynomial is defined as P of Z equal to, and these are coefficients. Whatever is written near that lines are the coefficients for the multiplication factors, GR, and this is GR minus 1, GR minus 2, G1 and G0. And the condition is that GR and G0 has to be 1. And the polynomial is defined as GR z raised to R plus GR minus 1 z raised to R minus 1, like plus plus up to G0. This is the polynomial. So if a particular say G R minus 1 is 0 means this connection, this switch is off. So there is nothing coming from here and going as a feedback, meaning the flip-flop output 1. And if it is 1, it means output of flip-flop 1 goes to this XOR and comes as a feedback to the input of flip-flop. And at each, and clock is provided, that is not shown here, at each clock edge, positive edge or negative edge, the flip-flop gets triggered and it transfers the data from input to output. So this is basically a shift register that you all know, and the output, you will get an output sequence. And the idea here is the input is governed by a linear combination, not a linear, it's a GF of 2, not our normal algebraic linear combination, but a GF Galois field 2 combination of other inputs, other outputs of the flip-flop, or basically other flip-flop outputs. Is it clear? I'll show you one example. Is it clear? Is it clear? Are you able to hear me? Okay. I'll show you an example. So you have 3 flip-flops, flip-flop 1, flip-flop 2, and flip-flop 3, and clock is connected, and output sequence is taken from the last flip-flop. So this polynomial is, the polynomial governing this circuit is P of z equal to z cube plus z square plus 1. This is from the, so I mentioned that, I just mentioned z cube, z square, z base 1 and 1. Mentioned that G3 and G0 has to be 1. So it is z cube is there and 1 is there, and then you can have a XOR here and a connection from here, but also the generalized structure, but that is not present. That's why you don't have anything related to z raised to 1. You only have, so you don't have anything related to z raised to 1. You have one coefficient, one term, z square, that is coming from here, because the feedback is only coming from the first flip-flop output and the third flip-flop output. So this is z cube plus z square. Z raised to 1 term is 0 and z raised to 0 equal to 1. It's 1. So that is mentioned here. I want all of you to by heart this or keep it in mind as a picture. And one way is to represent is by using the polynomial. Another way is to represent this LFSR by with a pair 3 1. That means feedback is from the third flip-flop and the first flip-flop. So this polynomial and this 3 1 in brackets represent the same. and modulo 2 adder is again XOR. Okay, we'll go to another example. I'm not going to explain this. I will give you some few minutes to understand and satisfy yourself that this is represented by this polynomial. The same line as we described for the previous example case. I'll give it a few minutes. If you have any question, you can ask. Okay, so 5432 is an LFSR with feedback from fifth. This is the fifth flop, fifth flop, fourth flop, third, and 2. So the feedback is from 5, 4, 3, 2. That's why it is called 5432. It can be represented as this set or the polynomial P of Z. Z raised to 5. The highest term will always be there, and the lowest term, that is Z raised to 0, that is equal to 1, that will also be always there. And then Z raised to 5, after there is no feedback from Z raised to 4. So Z raised to 4 is absent in the polynomial, and then Z cube is there. There is a feedback. Z square is there. Z raised to 1 is there. Clear? Okay. As I mentioned previously, for maximum sequence, maximal length sequence, PN sequence, the generator polynomial should be primitive. And this is, again, the proof of that is not required here. It is beyond the scope of this lecture. And that is, again, complicated maths in the Galois field theory. Flip-flops should be, and another important thing is, the flip-flops should be initialized such that all flip-flops are not 0 together. In other words, at least one of the flip-flop should be initialized to 1. If all flip-flop outputs are 0, then you will not get the sequence at all. Sequence will be 0, 0, 0, 0, all zeros. So at least one of the flip-flops should be initialized to 1. All other can be 0 or any value or any binary value. And the length is also called period. And if you have n flip-flops, and then the length of the sequence is 2 raised to n minus 1. So after that period, the same sequence repeats. This figure shows a PN sequence of 0 0 1 1 0 1, and it is represented in a polar NRZ format. But the output of the flip-flop will not be like this. Output of flip-flop will be binary data. So this is after a coder. So it is 0 0 1 1 1 0. This is one period, and then again 0 0 1 1 1 0 1. Up to this is one period, and again this is the second period. And this one bit is actually called one chip, CHIP chip, and represented generally by TC. So the chip duration is TC, 1 bit duration, and the total period is capital N into TC, and capital N is, or what I can mention is M flops, length of capital N is N equal to 2 raised to M minus 1. N equal to 2 raised to M minus 1. So if the number of flip-flops are 3, then the total length of the PN sequence is 2 raised to 3, that is 8, minus 1, so that is 7. That is the case here. Clear? Okay. Then we have some important properties for the PN sequence that are a must for our spread spectrum communication. One is it has to be highly random. So a third party that is observing the sequence should not be able to get the complete sequence. That is for secure communication. And another thing is it will have a uniform property, uniform distribution, like a normal white Gaussian noise. Well, sorry, not white Gaussian noise. It's like it has to be a uniform distribution, and then balance property will go to this one by one. Balance property, and then run property, independence, correlation property. Basically, balance, run, and correlation properties are the main thing that we will be discussing here. And unpredictability. By observing the sequence, you should not be able to, a third party should not be able to predict the sequence. That means it has to be highly random. And the autocorrelation function for this PN sequence is an important parameter. And this is the sequence, binary sequence. That's why we have represented it in summation form. Otherwise, in the continuous form, what is the autocorrelation function? Integral x of t into x of t minus tau dt. Autocorrelation function basically measures the similarity between one portion of the sequence with respect to other portions of the sequence. Okay. Here n is the length of the PN sequence. Now we will see what is the autocorrelation function of a sequence. Let's consider the same sequence that we just explained here in the previous slides. N equal to 7. Let's consider 0 0 1 1 1 0 1. This is the sequence, and this is the autocorrelation function. So how will you do the autocorrelation? Basically, tau equal to 0 means you are comparing the, or you are finding out the similarity between the same sequence, and the time shift is 0. Then you will get the maximum similarity. That is 1 by n summation cn minus k. And the summation variable is n equal to 1 to n. So it is when tau equal to 0, or tau, or here k corresponds to tau in the figure. So this is basically k. So for k equal to 0, you are comparing with the same waveform. In that equation, the autocorrelation function will be 1. Value will be 1. Then what will you do? You shift this left and right. Let's assume you are shifting it right. So what it will become? This 1 will come here. So the sequence will be 1 0 0 1 1 1 0. And then multiply with, do this calculation, and you will observe that, and the derivation is not required here, and we observe that its autocorrelation is for any value of k that is not equal to 0, the value is 1 by n. Not seen this autocorrelation being asked in any of the exams. If you want to actually see the derivation of this, you can see some textbooks. For example, BP Lapi, you can see advanced analog and digital communication. You can go through that if you want. Derivation of autocorrelation function. That will be 1 by n. So this is the structure, and again this is a periodic structure, and the period is same as the length of the sequence, 0 n into ts. Tc is chip duration, so this is periodic. What does this mean intuitively? It simply means that it is highly random. There is no correlation between one sequence and its time shifted sequence. That is what is a requirement in a spread spectrum. So it is similar to only that waveform and not to any time shifted waveform. That is why its correlation is negative value. It is minus 1 by n. That is very low. For example, n is equal to 2 raised to m minus 1 for a, say, a 4-bit shift register. N equal to 2 raised to 4 minus 1 equal to 15, and this value will be minus 1 by 15. So very small value. So as the length increases, say 10-bit means 1 by 1024. So it is, the correlation is very, very less. And another important thing is power spectral density. So these are, and how will we find out this? Fourier transform of autocorrelation function is power spectral density. If you see, its PSD has a DC, that is for frequency 0, it has the highest amount, and it goes to 0 at 1 by Tc, and again at 2 by Tc. It's like a sinc square function. And if you're interested, you can look for this in some advanced textbooks, in communication textbooks. But at least qualitatively, you should know this is the power spectral density, and this is the autocorrelation function for PN sequence. So if there is a question like this is the PN sequence, let's consider a case where n equal to 1024. So when k or tau equal to 0, what is the autocorrelation function? Same, there is no calculation required. It is 1. And for other values of k not equal to 0, what is the autocorrelation function? It is 1 by n, that is 1 by 1023. Straightforward. Is it clear? Clear? Okay. Now we will talk about some randomness properties. One is balance property. So in a maximum length sequence, it is a requirement for the spread spectrum. The number of ones and the number of zeros should be different by at most 1. And the number of ones will always be higher than number of zeros. So that is evident from here. So here in this sequence, what is the number of zeros? 1, 2, 3, and number of ones is 1. Number of ones is 4. There are 3 zeros and 4 ones. So that is the balance property. And second thing is run property. So a run is defined as the number of identical symbols ones or zeros basically within one period of a sequence. And whenever an alternate symbol comes, the previous run stops and a new run starts. So in this case, this is a run 0 0 similar bits. So this is the run. So this run has a length of 2, and this 1 is another 1 1 1. This is another run and it has a length of 3, and this is another run 0 length of 1. This is another length, another length, another run whose length is 1. So this run property says that half of the runs of each type. So you'll be having runs of 0 and you'll be having runs of 1. Half of the runs of each type are of length 1, and quarter of the runs of each type are of length 2, and 1/8 of runs of each type are of length 3, and so on. And that so on depends on the total length of the PN sequence n. So how far you will go depends on that n. Then the property 3 is correlation property that I have just explained. Autocorrelation from R of t equal to 1 for tau equal to 0, and since it is periodic at n to n like that. And R of t equal to minus 1 by n for any value of tau or k that is not equal to 0 or multiples of the period n. Clear? Okay. Well, these are there in the notes given, and this you can see the recorded video later also. Okay. Now let's take an example of a PN sequence, and how will you? So there may be a question in the exam, like a polynomial may be given, and you need to find out the PN sequence and see whether it is maximal length or not. So what is the polynomial equation here? This is set cube. So set cube plus set square plus 1. That is a polynomial. So P of set equal to set cube plus set square plus 1. Set cube is there. Set square. Set raised to 1 is not there. Set raised to 0 is 1. So initialize with any value that you want. Let's assume that we have initialized this with the 0, 0, 1. So output of flip-flop 1 is 0. This is 0 and this is 1. Now with the next clock, what will happen? Input to this XOR is 0 and 1. Right? This is 0 and this is 1. So output of that XOR will be different inputs, right? So output will be 0. Is it correct? Yes. For different inputs, output of this XOR will be 1. So that 1 is fed here. So with that clock, that 1 will go to the output. So with the next clock, this became 1. And the previous value that was 0 here, that went here. So that's this 0 came here and this 0 came here. This 0 came here and this 0 came here. Just for you to get a feel, I'll show that here. Like that, you have to do it for all the clock cycles. And the XOR of this 1 and this 0 is first output, and the third output is this one. So these are the two inputs. And this is the output. Okay. Is it clear? Like that you have to do for each of. Now the present data is 100. Now you will XOR this and this. So XOR of that is 1. So the next bit, this bit will become 1, and this previous one has come here, and this 0 has come here. Like that, you have to find out the total sequence, and finally you will come to know that after n period, that is after 7th clock, you will again reach at the same initialized value. So the sequence here is 1 sequence going out of the third flip-flop is 1 0 0 triple 1 0 1 1 0 0 triple 1 0. Is it understood? Clear? Because this is important and you can expect questions on this, finding out the sequence from a characteristics equation or a polynomial. Okay. And is it a maximal length? Yes. Why? Because its length is 2 raised to n minus 1. N is the number of flip-flops here. So 2 raised 3 minus 1, 7, and the length is 7. After that, it repeats. So how to see whether it is maximal length or not? You should get the same initialized vector. This one vector means it is the flip-flop outputs only after 2 raised to n minus 1 clock cycles, and it is maximal length. Okay. Okay, now a last topic. There is something called a gold codes, which are actually, these PN sequences are not directly used in spread spectrum communication. In spread spectrum, actually, we need a very large number of PN sequences to cater to very large number of users. So, for example, an example of a spread spectrum communication is your mobile communication, your 4G or a 3G, or previously you would have heard about CDMA mobile handsets, this code division multiplexers. All those uses the spread spectrum, and there, depending on the number, and we have huge number of users. So each of the users should have unique, at least at the time of communication, the people should have unique codes. So getting unique codes directly from the PN sequence is very difficult, satisfying all the property requirements. Then that is the reason why people have come up with something called a gold codes, which is basically generated from two maximal length PN sequences. And the normal PN sequences have some poor cross correlation. So we'll come to know, and we'll discuss about this in the spread spectrum. So one requirement is that the cross correlation between different PN sequences generated in CDMA has to be ideally 0. Basically, there should not be any similarity between one PN sequence and another PN sequence generated. But that is not always possible using our normal PN sequence generation. So this we have come up with this gold codes. So you just read through this. Okay. So I'll just show you how the gold code is generated. So what we want is, we have two PN sequence generator. So both of these has to be primitive polynomials, should be represented by primitive polynomials. So this is a maximum length PN sequence generator with 5 flip-flops. So the length of that is 2 raised to 5 minus 1. Similarly, this is also another maximum length sequence with another polynomial, and length is 2 raised to 5 minus 1. Like that, you can have any length. Now we will XOR that, and that is the gold code. So the length of the gold code again will be 2 raised to n, and the number of flip-flops 2 raised to n minus 1. So here 2 raised to 5 minus 1, that is 31. 2 raised to 5 is 32, minus 1 is 31. And but what is interesting here is that you will get 2 raised to m plus 1 different sequences by just this polynomial, by just this arrangement. How many sequences will you get for one part of this? You will get 2 raised to m minus 1, right? Here you will get 2 raised to m plus 1 sequences. So you are getting huge number of different sequences to be used in CDMA. Just go through this. This is what I have explained now. If this were not there, how many sequences will you get? So the length of the sequence is 2 raised to 5 minus 1, that is 31, right? So since the autocorrelation is like 1 for tau equal to 0 and minus 1 by n for other things, you can generate different sequence by time shifting. So by time shifting, you can shift sequence. You can shift 2 raised to m minus 1 times. So you can have that many sequences.
Sir?
But in gold codes, you can generate different gold codes by different initialization of these things. You can initialize this at one particular value, and this at another particular value. You will get another code. You will get one code, and initialize with a different code in the top one, and another code in the bottom one. You will get another. So like that, you have that many combinations possible. So you'll get huge number of codes. That is important about gold code, and which satisfies the required properties for spread spectrum. And just an example problem here. Let's consider a maximum length PN sequence generator which has 10 stages, and the chip rate is 10 raised to 7. One chip is 1 bit, 10 raised to 7 per second. So find the PN sequence length in seconds. How will you do that? Chip rate is chip per second. is 10 raised to 7 chips per second, and n equal to 10. So period or length of the PN sequence is 2 raised to n minus 1, that is 1023. And each chip is, so 1023 chips or 1023 bits in one period. So each period is 1 by chip rate, 1 by 10 raised to 7 seconds, right? So that is 102. So it is total PN length sequence is 1023 into 1 by 10 raised to 7. It is equal to 102 microsecond. I think this is given in one of the assignments or as a homework problem. Okay, this is very simple. Okay.
സാറേ അറ്റൻഡൻസ് ഇടാൻ പറ്റുന്നില്ല. ഹലോ സാർ.
So with this, we will wind up today's class. Thank you.